Okay. And we are back with the seventh episode of JEHC. IFS front suspension design stuff, aspects, things along those lines. And my name is Jason Elvis Hurd. This is the seventh installment, like I was saying. I knew this was going to take some time to kind of go through this rough outline that I have. And there's still tons of stuff I still want to cover that's not even an outline, stuff that's obviously a little bit more in depth, a little bit more detailed per se. But let's keep moving forward. My name is Jason Elvis Hurd. I am founder of Tech Consulting Inc., design development, blah, blah, blah. And same with DIYoffroad.com, digital asset marketplace for individuals like myself to sell digital assets that are non-proprietary, so guys can cut them out and put their stuff together and build their own cool stuff. From full bulkhead things, I mean, these are definitely some of the most popular files, like this one right here, the Stage 1 truck front bulkheads. These are incredibly popular front ends for a lot of guys that want to center mount their trucks. I have them in several different track width setups, and they are plasma table friendly, meaning they are designed and developed to be cut on plasma tables, and either they're simply MIG welded together, or you can do them out of laser cut and TIG weld them together out of like 4130 as well, or MIG weld 4130 for that matter. Again, that's totally fine. So again, there's another misconception. You can definitely MIG weld 4130. It happens quite often. And if you're going to do so, most are doing that with ER70S rod. Although my personal preference, if I'm MIG welding 4130, would be an ER80S D2. You can get that in a MIG wire. It's also typically 15 to 18% higher in cost than a 70S, but still pretty good. So again, there's just something simple. We're going to get a question I'm going to answer real quick on the some lower stuff and diagonal internals that someone asked me about, because I did mention that last time. I just never put a picture up. I did actually go and pull pictures for that. And then I'm going to continue on upper arm fabrication style and some of the bits that have to do with that. Then we'll move on to some machined upper arm bits, and we'll see where we keep going with this. So let's dive right in. So one of the questions I actually had a few questions, and I completely botched writing the other ones down. If I remember them, I will try to remember them. So let's review here. This is a kind of a standard-esque style lower arm where, let's pull up the other pack so you can see kind of where I'm going with this. So let's go to here we go, like one of Dave's arms. So these sections here are in essence hollow. You know, they're a very simple setup, and like I was saying last time, it is designed in a fashion that coincide with our shock mounts and line up appropriately, and then everything comes to the bearing cup. So Dave has done that. There's an ID arm. Here's a Herbst arm, very similar in format and style, these shock pocket style arms. And so what I had mentioned last time, let's see, one of the older Herbst arms, there we go. Again, same deal where it's hollow. And so what I mentioned last time is in some applications where guys had asked me to have a little bit more of a robust arm. Now, the thing is that these arms are not inherently wrong or incorrect. All that's happening and what you were seeing here with these arms that have these sort of shock pocket hollow-esque sections is that they're venturing now into what would be considered like race shit or true race stuff, in the fact that these are consumables. So if you're trying to build a legitimate race program, team, etc., there's very valid argument on the side of the table to make the components as light as we can while maintaining a very mid-range or low-level range of resilience to some degree, so that it's considered a consumable for every season. And there's nothing wrong with that. In my opinion, if you're trying to campaign a vehicle in this realm and do so to be competitive, having to replace a lower arm, so to speak, is something like this every season, not those per se, but something like this every season is, again, like totally acceptable and arguably better because you can pull out 5, 6, 7 pounds here, 8 pounds here, 10 pounds here, get these arms relatively lightweight. And, with the ability to weld these appropriately with a proper rod and treat them appropriately, you'd be surprised how thin we can make this stuff and how little we can add to the arm to get us to where we need to be, or where we want to be, so to speak, relative to a robustness and the factor of survivability through the season. And so with that said, like I was saying, if you have to replace arms every season, that's not bad. I mean, hell, if you have to replace arms partway through the season or halfway through the season, that's kind of like one of those deals, like this is a consumable in these high-level racing programs. Now, some people agree with that. Some people obviously don't agree with that. But if I was working towards a full kill race program, my expectation would be to design components in a mindset that one season is all you're really expecting those components to go. And so you can do some cool stuff between, and I'll get to how I like to do treating and things like that, because there's obviously different ways to approach treating components. Some obviously are more expensive than others, but the point being here is, so this style has that sort of hollow section in these parts. And so what I had mentioned last time is on occasion when I would be asked by certain clients, etc., about adding some robustness, so to speak, to this with trying not to exceed weight too much, is we're putting diagonal ribs in these sections here. And it doesn't add a lot of weight, but definitely helps in the robustness. And so an example of that I pulled is this arm right here. So this is a replacement arm we did. And so specifically trying to maintain the robustness of it. These are, in essence, that shock pocket style arm with a hollow. And I've done, if you look at the other arm sessions, like the lower arm previous episodes, episode 5 and 6 of this IFS design stuff, you'll see I have a bunch of different styles that I design, especially like my tube lower arm style, which is my preference. I just like that. But that doesn't mean that anything is wrong with making these weak or consumables. As you get to the more pinnacle level of racing, you're going to see that these items are more than acceptable, but the argument could be valid that it's a requirement to shave off unsprung weight appropriately, because if you can't afford to replace all the suspension on these vehicles every season in that top level classes, you really shouldn't be trying to compete there. Let's be perfectly honest. That's how competitive it is these days. Just like you wouldn't run the motor for multiple seasons, or a gearbox and other aspects of that nature. And in doing so, if we can cut down 500-600 pounds total of the vehicle, and let's say several hundred pounds of that is unsprung weight, that's a huge advantage. These vehicles are at that competitive state that shaving seconds, shaving minutes off of stuff like a Baja 1000 or a 500 or a Mint 400 or Vegas to Reno. These are very important chunks of time that the lighter the vehicle can be, the more aggressive you are with designing something in a lighter fashion per se, can yield positive results when it comes to winning races, because attrition isn't necessarily the case as much as it used to be, or at least as I remember 10, 15 years ago, where survivability was the primary issue with guys not finishing. These days, it's on the top level, so to speak. It's about speed. So attrition is first and foremost. Obviously, you have to finish, but now there's so many people that can finish. Now it's more about not deteriorating time with bullshit like pit stops or bullshit like the truck just simply is a pig, So in essence, to combat that, you're design developing components and things like that, using things like heat treating and all these other cool stuff that you can then thin out the material and lighten up the component and the arm, and do so in a fashion that obviously is not going to stress you too much on the robustness. And so with that said, like I'm saying, in those aspects, those arms are totally appropriate. And I have seen those arms wadded up. Everyone has. That's in the racing side of the industry. I'm sure you could find pictures of them somewhere in that style. But the fact that you're trying, or someone were to say that is incorrect, or they fucked that arm up, or whatever, again, I don't buy into that, because I think they're not understanding the reality that this caliber of racing comes to in these competitive fields, where the shaving of seconds and minutes is a priority. So again, this is for top-notch-esque stuff. So the vast majority of you guys will never have to deal with or be concerned with trying to lighten an arm to the point where it is considered a consumable. But when we're trying to build these competitive race vehicles and the competitiveness of today, that is borderline a necessity to some degree. And some will agree with me on that, and some obviously don't. So different strokes for different folks and builders and things like that. But anyways, where I'm going with that is I had mentioned that I have done diagonal internals in sort of this similar style arm. And so this is what that looks like. Let me just show you. So that's what the arm looks like, in essence, from the outside. So you would think it's like hollow, right? Because you don't see the stuff. Well, in essence, there are diagonals in there, and they kind of come cross to the two weld seams, because that arm is basically like two L's that come together, kind of like this, you know? And there's a diagonal between those L's in that section. And so that's what I'm referring to by another trick I deploy to just add a little bit more robustness with not adding a lot of weight into that, you know, basically exactly same style shock pocket style arm. Again, and the argument can be made that this is totally not fucking necessary. And I get that too. I'm only adding, you know, maybe 1.5 pounds, maybe 2 pounds per arm. But again, valid argument that me doing so is considered like fucking wrong or pointless. But again, a lot of what we design for and things like that, there are so many different applications and components and things. And so like then the other side of the argument could be that if you were not going to heat treat this arm, adding those diagonals would be a very good thing, because now you're adding to the robustness, et cetera, et cetera. Whereas I could get away with not adding those and treating the arm, et cetera. When I'm saying treating, I'm referring to heat treating. And like I said, I'll get to that. That's like a few more sections. I have a few bits to go through my outline until I get to the heat treating stuff, because I'm just trying to cover generalized with components. So just wanted to touch on that real quick so that you guys understood what I referred to when I said diagonal internals. And those are these bits diagonally. Now the front of the arm, or I'm sorry, the exterior of the arm towards the cup is obviously a little bit more standard, where we're carrying, you know, the ribbing from the shock pocket forward into the bearing cup appropriately. As you can see, the forward face of this forward shock pocket comes and grabs the cup here. This is actually a mid section, a mid face. And then the forward face of the rear shock pocket comes with this internal rib here. The rearward face of that shock pocket comes to the backside of the bearing cup. And in this specific arm, we've got the bearing cup angled to both travel and to caster. And it is built in a shock pocket format. So in essence, you would build the shock pocket first. I don't have a good picture of that. But the point is, again, it's just various different ways to complete the same task. And as you get further and further into the more serious race stuff and the competitiveness that is off-road racing, especially these days, there are incredibly valid arguments that arms, lower arms, upper arms, uprights, things along those lines, housings, links are a season consumable, and arguably lower than season consumable, i.e. mid-season, those items are getting replaced out of necessity for both the design and engineering standpoint of building something as light as you can and robust as you can. And you are obviously going to be utilizing very specific materials, very specific welding rods, very specific welding techniques, and very specific treating techniques to accomplish that task. If you're not going to be treating the stuff and you're just doing standard issue chromoly with ER70S rod, again, that doesn't necessarily mean that that is wrong. A vast majority of guys are doing that. Most likely than not, you're going to lean a little bit more towards the robust side in the design department intentionally, so that you don't run the risk of under-engineering the component. And typically speaking, and I know this, I don't want to offend anyone in that, if you are leaning on that side of the table, i.e. you are not properly welding, not properly treating the components, not properly fixturing the components to do so, and I'll dive into the specifics on that, you are building components in a lower budget sort of category. Now, that doesn't mean that it's crap or inappropriate. What I'm referring to is when you start taking these extra steps, you start blowing the budget out a lot. So a set of lower arms could be something as simple as, $1,500 of chromoly laser cut and TIG welded up with some ER70S rod, might take you a few days, etc. Now you want to take that a few steps further, engineer an arm that might take a little bit more to design in the computer, because we have to have a little bit more thought into how we're laying it out and setting it up relative to its specific layout, so to speak. And we're going to lighten the arm up. Then we're going to have that laser cut. Then we're going to weld that up with a non-ER70S rod. There's a few other rods, and we'll dive into that too. Then we're going to have it treated. And then you also have to have the appropriate machined bits and tooling required for that. And you arguably might post-machine it. So those two avenues, although can complete the same component, and there are trucks that run like that and win races in either of those avenues, the latter with the treating, the post-machining, the proper welding, is going to be significantly more expensive. And in some situations, you could have literally the exact same lower arm and it would be triple the cost. And so for obvious reasons, everyone, including the guys in trophy truck class, they have budgets. Some of those guys have budgets to where it is not a problem to go through those processes. Others, that would be considered something that would be a trade-off in their racing program. So they are not necessarily dedicated to going that extra mile, so to speak. And again, that doesn't mean that those guys are doing it wrong. It doesn't mean that they're idiots or anything along those lines. It simply means that in every situation in life and racing especially, at the end of the day, that check has to be cut by someone. And when that check, becomes significantly more expensive in certain sections of the race program, you have to mitigate that appropriately. And so if you can't justify having to go those extra steps and, maybe decrease some of that, what would be considered the competitiveness of some of these components, well, you got to keep that in mind relative to your budget. So again, different strokes for different folks. It doesn't mean that one is worse than the other, because the inverse side of the table is we also have guys where I make arms that are significantly more robust than some of these lighter weight arms where we are, in essence, doing everything we can to design it in a fashion to shave ounces, not pounds. And, there are definitely arms where if I lay them stacked next to each other, I mean, they are very similar, but one will literally be double the weight than the other, and it's some of these aspects. Now, those would lean towards the clients that, in essence, do not view or prefer to have suspension components viewed as consumables, i.e. they want lower arms to last them multiple seasons as opposed to a half season or a full season. So with that said, let's continue on to the upper arm fuckery. Where we left off last time was we kind of, were reviewing different bits and concepts with the design. Now we're going to dive into some elements of fabrication, so to speak, in the design. So we've got, like the Oreo style. Let me just get this open. We'll start with the simple stuff first, work our way up. See if I have those in here. Yeah, so here's some of the more simple stuff. So here is, and I went through some of these with the internals. So yeah, this is like the Oreo style where the plates in essence just click together. This is part of, like I was showing you before, the stage 1 front bulkheads designed to be plasma table friendly. Very simple construction and great for guys that have never built this type of stuff before because they are for the most part self-fixturing. They go together relatively quickly. They are easy to weld up. They work great for MIG welded applications. The vast majority of the guys getting or buying that stuff is going to be MIG welded. And this would be like an upper arm for one of our truck applications. It's all 1/8 inch material. Some guys will cut these out of 48130. Some guys will cut them out of mild steel and MIG weld them. And some guys will TIG weld them. But the point here is this is that Oreo style where you just have two top and bottom plates that basically snap together. And then you weld up all the outside and the external ribbing. And so that's a truck one. Here's a buggy one where I just run an interior rib that comes down and through. Something cool to note is, although it might be hard to see in this picture, it is a little hard to see. So this internal rib here comes all the way down and it pokes out right there. So what ends up happening is you end up welding that internal rib with this external piece kind of uncovered or not there per se to this bearing cup real quick. And then you snap in this last little square right here, like a cap piece, and weld it up. So that this rib comes from front pivot all the way. As you can see, it gets welded to this front upper arm pivot all the way to the bearing cup. And then the other bits, again, this is an 1/8 inch or 095 arm. These are for buggies, so like a 4-seat buggy. The guys who do this out of mild 1/8 inch or 095 4130. And obviously you can do like 095 4130 for like a 2-seat buggy type of application. And this, again, is another plasma table friendly Oreo style arm where we are minimizing the complexity of bends, minimizing the complexity of forming in to specifically make this arm a lot easier for not, more of the novice guys, more of the guys that are doing this stuff for the first time. Here's another version. This is like a Rock Racer upper arm that we sell in our all-wheel drive plasma table friendly front end. Again, this is an Oreo style format. This is thick as fuck. I want to say this one can be 3/16 or 1/8 inch for the top and bottoms, depending on the client preference. And definitely most of the guys doing this stuff is going to be MIG welding them. And most of them are probably going to be doing this out of mild steel. So again, just something that is kind of like the entry-level fabrication. You can see some of the tricks I deploy here where these are all straight plates, so there's no bending. And so what you can do is you can weld up this section from the interior side once that other top is on to minimize warpage and things like that. But now you're tying this internal rib to these guys to blah, blah, and just getting a nice structure. So we're not going to ever leave this as like just one hollow fucker, like that's just not going to fly for this type of stuff. And then, again, here's a sand truck arm. Now these are, lightweight-esque chassis that you would see like a sand truck. So Glamis-esque stuff. Again, these are 1/8 inch or 095, mild steel or 4130, depending on how the guys want to cut them. MIG weld friendly, plasma table friendly, super straightforward. And this rib comes from this bearing piece all the way up. It gets welded on it, pops out on the other side. Let's see if I have a picture of that. And I don't. But anyways, it pops out on the other side, and it's this still same Oreo deal where it snaps together and creates a sort of ridge to weld. So these are very simple to build, very simple to weld, very fabrication friendly. So just a few different variations of what we call Oreo or plasma table friendly arms. Now let's go to stage 2 or something that's a little bit more complex, like some of the on-edge welding arms, like this arm right here. And, interestingly enough, this is a knife edge arm. So the knife edge arms are a little different. In essence, we're creating this sort of V structure in the front. I call it a knife edge. Or it's been, I've heard it called many things, but lately it's been referred to as a knife edge, primarily by Robbie Woods, who invented the knife edge arm. And the guy is just talented, because to be able to invent the knife edge arm 20 years after the vast majority of the industry was already doing it, that takes some fucking talent right there. But God, credit where credit is due. So anyways, these would be on edge welding arms. So these obviously have a little bit more forming involved. They are a little bit more complex. When we do sell these sort of arms, they do have a fixture that helps get everything built and aligned, whereas these plasma table friendly type ones, we don't typically fixture them. They're kind of self-fixturing, and you kind of use the bulkhead and double check and go back and forth. But again, these are a little bit more on the budget friendly-esque side of the table. So when you start, you get guys that are building like one-off things here or there, it's a lot easier to mitigate and do that yourself, so to speak, as opposed to building elaborate tooling and fixturing, which often will end up costing significantly more money than the arm itself. So that is a misconception to some degree. That just reminds me. That other question someone asked me was something around those lines, cost. And now it's escaping me. God damn it. I will... machined versus plate. Weight, lightness. That's what it was. Let me make a note so I don't forget that. We'll get there. Machine weight. Or, we can just cover that now before I get too far into this. So one misconception is, again, like I was referring to with some of the heat treating and being able to thin stuff out, is that machined upper arms are lighter and stronger. Well, yes and no. Yes, in that the majority of the stuff, a lot of upper arms and things like that can be done in a fashion to where the fabricated arm ends up heavier than the machined arm. But that is the case in the more budget-esque or friendly stuff. When you start diving into what I was referring to earlier, and this is the same for upper arms just like lower arms, when you start diving into utilization of heat treating, proper welding, and thinning out material a ton and then designing appropriately, you're going to end up with a much better component fabricated than machined. So it's a huge misconception that because you're machining upper arms, that is both lighter and stronger, and it's not even fucking close to the case. A real race car per se, and if your real goal is strength to weight ratio or robustness to weight ratio, you're not going to do machined upper arms. You just not. Nor are you going to do machined uprights, just to be crystal clear. And again, the reason that crosses that bridge is because in like an upper arm instance, you're going to be able to make a lighter and more robust upper arm from a properly fabricated chromoly material with a properly welded rod and treated properly than a machined equivalent. That's the reality. Now, if you're not doing those steps or taking those steps, then yes, the argument can be made that the machined arm could be lighter and possibly stronger, possibly. But I just want to nip that in the bud, that simply because there's, typically speaking, machine components will end up being heavier than if your goal is specifically for trying to have the best race component. You're staying away from machined bits. I'm sure that's going to piss somebody off, but the bottom line is machining actually falls onto the side of the table of a cost incursion metric for the builder as opposed to a performance metric. Typically speaking, when you start machining components like link arms, upper arms, things along those lines, uprights, what you're actually doing is the builder is mitigating too high of a cost incursion and sacrificing performance. So, there are caveats. So like in the all-wheel drive uprights, the portal uprights, the machining of the upright would cross that bridge, but that's the exception. But the norm is fabricated uprights can always be done, and fabricated upper arms, fabricated lower arms, if you are going to design them properly, thin them out, weld them properly, heat treat them properly, they're always going to end up being lighter and stronger than a machined machine component. The trade-off here for the builders, and why I say it's a cost incursion, is because it is much cheaper for the builders to machine these components or have them machined than in essence have the fabricators in-house fabricate the components, typically speaking. It doesn't always work like that in all situations, but that is not necessarily an odd thing if that were to occur. The other side of the table in the builder aspect is it's a bling factor. So although you sacrifice performance with these big blingy machine parts, the thing is people do like that. And, again, I'm on the fence. I think both of them done properly can be really fucking cool. But if I was building more race car-esque stuff, I'm going to lean significantly heavier to fabricated chromoly, properly welded and treated components any day of the week over anything machined. But, again, it's different strokes for different folks. So it's all a variable. And especially when we start getting into the rear suspension stuff and we start diving into like the link arms and things like that, where you start to see these multiple pound differences, 10 pound plus differences in machine and fabricated components. And I mean, the fabricated ones are definitely lighter, properly done, mind you. And you'll start to understand that, this stuff adds up, et cetera, like I was referring to before, in the competitive aspect, or where are you going to be on the competitive aspect. So that was just one of those things, one of the questions that someone had asked about, what do I prefer, machining or fabrication? And again, it depends on the client preference. It depends on what my goal set is. Both properly done can be equally badass. So there's no good way to say that one is better than the other. It's a specific scenario where one can be better than the other or worse than the other. And so you have to stack up apples to apples, not just these generalities, so to speak. So with that said, back to stage 2 upper arms and an edge like welding. So these have an edge, so to speak, where we are welding them. So they're not that Oreo style that creates that sort of T-surface. This does create a much cleaner look, a much cleaner arm. These are a little bit more difficult to fabricate, although we do put these little alignment tongues in there, which help a lot because it helps you get like a good tack weld in there, and then you can start tacking along the arm. Then you can sand down those high spots and then lay your fucking root pass, lay your fucking cover pass, boom, and it'll look all nice and pretty like the Instagram welders. And so these arms, these are like our stage 2 truck upper arms. These typically are just going to be 1/8 inch material, although you could step these down to much thinner material if you're going to appropriately weld them and treat them, which, you know, I've done that too. Now, these do have fixtures, like I was saying, unlike the stage 1 type stuff for some of those Oreo-based arms. These are built in a fixture to make it a lot easier to assemble and to increase the accuracy, but between the forming of these arms, a little bit more complexity, which means more time, and the tooling, these arms are like double the price to build than what that stage 1 stuff is. And the other factor to keep in mind is these are designed to be chromoly only. So you should not be cutting stuff like this out of mild steel. There's a look at that arm, that lovely fucking brand new ripped off knife edge. And then those sort of slots that are in the middle right there for carrying those ribs forward to the bearing cup and appropriately. So in other words, we're not ending up with a hollow arm at any point in time. And then you can see that this is a jam nut style arm, so we're appropriately wrapping those bits at the ends. Here's another one. This is a lot more old school. This is the arm I did for Ross King, and it's kind of different. I don't like this style as much. They're a little difficult to put together, but basically the sides create sort of that other T, so it's not necessarily an Oreo where it comes down from the top. It's like the sides click in, and then the sides create this sort of T lip to weld. I know it might be hard to see, but again, another style. I would say this is a little bit more old school as far as styles go, but some guys do like this. It's just not my personal preference. And then these bits here are for the slapper arms, etc., etc. Yep, there's another one. Here's another style. Let's see. I just want to make sure. So PDF on edge. Tube and plate. Again, I am not the first to do tube and plate stuff. It's kind of a classic style that a lot of guys have seen. Let's see. I think Dave has some pictures. ID Designs, because he's done tube and plate variants definitely longer than I have. Granted, he is older than me, to be fair. But I just want to show you another way of doing it other than what I was going to show you some of mine. That's just tube. And I am a big fan of the tube and plate style. Here's an arm. This is a good example of an arm getting ready to head to treating. So these are slugs in there, ready to go for a treating. This is going to basically be a spreader to hold all rad. And in doing so, it's going to maintain the distance here and maintain what we want so that this does not fuck off during the treating process. And we'll get into more of that. I'm trying to find an example of a two-plate upper. Here's one. I can't really zoom in. But anyways, the point being is it's a partial plate structure for this main, and then it's a tube cross and a tube main coming down. And so again, it's like a hybrid. Now to build these, you definitely need to have a fixture, so to speak. So like here's a version I did for someone for a trophy truck, and it is a tube plate arm. In essence, the structure that is being created is a mixture. So you've got sort of this tube cross and tube coming down to the main side of the front of the bearing cup, and then this platework structure that comes in and complements that. And so, again, just another way of doing it in a tube plate style. Here is a tube with a tiny bit of plate. This is the upper arm of that Jake Berkey rock racing buggy. These are actually 250 wall tubes. Really gnarly shit. Turn and burn with some 1-inch rod ends on the chassis side. But if you know what I'm referring to, these are not desert racing applications. These are rock buggies. I mean, these are these gnarly rock buggy things that Jake Berkey does. Machine stuff. Oh, there we go. There's one of Dave's arms. Again, tube and plate style construction. And like I was saying before, is when you go down this route of minimizing wall thickness, maximizing the welding process and the treating process, you can make these lighter than an aluminum component and definitely more robust. But the trade-off is this is more expensive to do than machining an aluminum upper arm. That's just the reality. Like this is a non-heat treated upper arm off of older Jimco. This right here, I don't remember whose arm this is. I think this is a class 1 arm I did a while back. Here's another tube and plate arm I did on a 7200 build for John Addison's truck. This is the Izzy Fabrication upper arms. Knife edge. Classic knife edge here. These are all 1/8" plates. Izzy does not do any heat treating or anything along those lines. I'm pretty sure he's just doing the standard issue chromoly plate and ER70S rod on these, which is what the vast majority of guys do. Let's see. I think I have some of my T4 style in here, which is another tube plate style arm as well. There we go. So another tube plate. Now in these ones, I actually support this with another plate coming in here, and that does allow me to thin the arm material out a little bit more. And then what I also do is this welds. This has some slots that weld to the tube. So it's kind of creating this sort of hybrid tube plate-esque arm deal, and these are like our T4 upper arms, and it's just another style, different strokes for different folks. But yeah, it's just a different way of kind of building the same style arm, and all tube and plate. This is all plate on edge upper arm for an all-wheel drive, which actually, I have more news on that stuff coming up here soon. And then so yeah, let's see. Tab and slot. Oh yeah, so the same things apply tab and slot wise for these guys, just like the other applications. Like I mentioned through the lower arm stuff, I kind of want to do tab and slot stuff that is going to be, let's see here. I wonder if I had any. There's not good pictures, but the point being with the tab and slot part is this doesn't really differentiate from what I had reviewed previously with the lower arm stuff, where you want to have larger weld sections, then smaller sections in between, and then larger weld sections. Or you want to have continuous weld so that the rib has a lot of connection, so to speak, with the top plate. What you want to avoid are like a 1-inch weld and then a 2-inch space and then a 1-inch weld and a 2-inch space, because the rib is barely fucking grabbing the top plate. It might as well not even be in there. Like I was saying, I typically like to stick to having, several inches of weld space, like a 1/2 inch of space, and several inches of weld, and like a 1/2 inch of space. And so that's a tab and slot. Still applies to the upper arms or basically any position you're doing tab and slot stuff in. For depth, it's the same thing I was saying before. I like to be below 50% of the material that the top arm is. So if it's an 095 top and bottom plate, so to speak, that you're tab and slotting into, you want to be at like 40,000s, 45,000s, maybe 50,000s on the high side. And even in like 1/8 inch or 125 plates, I would still go to like 50,000s or less. Like you can always go less. You just have to put more material into that sort of groove. So you might have to really focus on a real good first root pass and then a good second pass. Whereas the argument could be made that if you made that tab higher, you could only single pass it, but that's not great because you're not getting great penetration with the side plate, the material in that groove. So again, like I'm saying, this is the same stuff that applies to what I was talking about. Same thing with pocketing of the lower arms as well. Like in this one here, you can see I am doing triangles. That is one method of pocketing. And then in some other upper arms, I'll do stuff that's a little bit more simple, like circles. Again, you're just taking some weight out that does not necessarily need to be in there. Same rules apply for this as did the lower arms as far as the internals and the webbing go. And same thing apply here with wrapping the cup, like I have previously mentioned. You're wrapping the cup by making these top and bottom plates tangent with the OD of the cup. Creates a nice wrap surface, and it creates like a nice flow and transition from the plate to the round. So it just becomes a nice smooth deal. And you don't have like a step in there because you have a mismatched top and bottom plate from the base structure or core structure going into the bearing cup. Internal ribs and thicknesses. Again, that stuff all varies on the arm. This arm that's here. This is the one I was just referring to. This arm is, again, this is still kind of review, 1/8 inch or 0.95. Same with the internals. I've done them both ways. If you're doing chromoly and treating it, 0.95 is plenty fine. Argument could be made for thinner, but most of the guys are going to cut stuff like this out of 1/8 inch material, non-treated, and welded up out of 4130 and like ER70S rod. That's the most common. Let's see. So internal ribs and thicknesses, bearing cup to chassis side, internal rib connection. Yeah, we went through that. UTV upper arms. I did mention that last time. I'm going to do a whole section on UTVs. I feel like there's way too much to elaborate on. Oh, let's dive into some slapper arm stuff. So we have mentioned slapper arms before. And I explained to you kind of what they do in relationship to bump stop, but let's just go about a few slapper arm fabrication methods. Where are those? I don't remember where I put that. In shock? There we go. Okay. So here is one method. And in this method, basically, you have a machined piece that you are making to match, so to speak, the... sorry. I'm just trying to get adjusted. You are machining this piece that matches the upper arm. And so what that is a chunk. Typically, that's going to be 4130. And this outside diameter will perfectly sync with the bearing cup of the upper arm so that at compression, etc., it's a nice, smooth connection. And it can be metal to metal. It is not uncommon that it's metal to metal because most of what's going to be taken up as far as force goes, it's going to be right into this little slapper arm. In this example, this is also a tubular built slapper arm. And again, you can make these out of some pretty thin material. I mean, this can be like 1 inch 0.65, maybe arguably 0.045 if you're going to treat it, etc. Because all it's really doing is just holding the location of the slapper cup for the bump. It's not really taking a lot of force in those sort of other directions. There's a little bit of that slide force it has to account for, but for the most part, the force is just going directly into that bump stop. So it's more like a guide / locating-esque arm, so you can get away with some really thin material and small stuff. See, as you can see in this image here, this aligns with the top of the bearing cup, and so it'll contact the top of that bearing cup appropriately. And again, some guys really like these, some guys don't like these, just different strokes. Here's one I did for the Ross King arm where this one did not contact the cup. This was actually a Delrin pad with some laser cut plate, so to speak, that contacts right here, right below the cup. And this was really thin shit, if I remember correctly. It was like 0.45 chromoly plates. And then these are tiny rod ends, like 3/8 rod ends. Yeah, I'm pretty sure it's been like 10 years. It was a while ago when I did this. But like I'm saying, is it doesn't need to be anything crazy or heavy or anything. Again, you don't want to just start indiscriminately adding weight for cool factor. There's no reason to. And this is one of those old King 2-inch slapper bumps. This may be some of the first ones they ever did. I mean, we're getting back to a while ago now. And I designed this for Ross King on his luxury pre-runner of King Shock. So this was a little idea he had per se. I just simply completed it. It's not like I created these sort of slapper arms, but there were fucking dudes doing this shit 10 years before I was. And I was doing this 10 years ago. So, yeah. And again, here's another side shot we made. I think these were light racing 3/8 rod end receivers back then when I did this. So just another way of doing it. Super simple style. Here's another way where the slapper arm is grabbing the lower end of the shaft of the bump stop, and then it's using more of a traditional bump stop pad end to contact the upper arm. And again, just a simple tube. I think it's on the Simon & Simon truck. Yeah, a fucking decade before I was doing anything, for sure. So, again, no claim to inventing any of this shit whatsoever. And let's look at the RCRO one, because that's another cool one. Here, again, another old school style of a very lightweight tubular slapper arm. Like, that could be fucking 0.45 wall or 065 wall. It does not need to be heavy at all. It is simply just guiding that bump stop from wanting to basically slip outboard. So it's all just, more or less tension forces on those fucking tubes. And it's just set up to contact, right there at compression. And again, it leaves all this force coming into this bump stop. And I really do like slapper arms. I think it's cool. Some guys don't. Some guys don't like the addition. There's definitely argument for both sides of the table. And typically, you're seeing this stuff more in the race truck type applications simply because of cost and dynamics with that, as opposed to like long travel stuff. Although, like Camberg is starting to incorporate these slapper arms into some long travel based stuff and things along those lines. So again, different strokes for different folks. Another way of doing it to some degree. So let's review another style with upper arms, and that would be some of the long travel upper arm fabrication styles. So let's pull up some guys from that. Let's go Blitzkrieg. So Nate does it long travel stuff is done differently, and inherently speaking, we'll get into the machine stuff too, but here's like one of his fabricated ones. Oh, you can't zoom in, cunt. Anyways, you can hopefully you can see it. It's an Oreo style arm where it's a vertical bearing on the upright. And now the reason for this, and the reason a lot of this is common in the long travel based stuff, is because you end up with such a stubby upper arm that getting a horizontal bearing doesn't really fly with the travel you're trying to achieve. So instead of limiting yourself with a horizontal bearing, you'll go vertical bearing in the upright and then make the upper arm in this fashion. Again, very common for long travel kits. And you do so to still have the travel, and then the turning radius is, in theory, you do lose some of that, but for the most part, these trucks have enough turning radius to where it's not the end of the world, especially in the all-wheel drive stuff like this. You're kind of limited by the CV anyways, so the argument could be totally valid that vertical bearing is, irrelevant to some degree. If your argument was about turning radius relative to wheel travel and a horizontal bearing. But like I'm saying, in a lot of long travel stuff, it's going to always be a vertical bearing up top. The simple fact is the length of that upper arm means that we get a lot of upper arm degree change through travel, that camber curve. And if you have a horizontal bearing, it's going to limit it way too much. So mitigation of that. And in this fashion, like his style kind of have this sort of platework structure, and then it comes down below the platework structure to grab the upper arm. And that is an old school style. You can kind of see it right here too. It's a little bit of an old school style, although another variant of that, he's kind of got this one where the bolt is more in line with the arm. Both of them can totally work. Both of them have been proven. And again, they're just simply different styles. Now, he does machined ones too, and we'll get into machine stuff. But here's a good example of another fabricated one, an Oreo-style arm, so to speak. And these are like production-esque long travel systems. So, you are sacrificing some of that wazoo-ness by doing this Oreo-style and MIG welded, but, you're also not spending $20,000, $30,000, $40,000 on a front end, so to speak, that, in essence, these long travel kits are more of the bolt-on, street-driven, daily driver type stuff. So again, totally different strokes for different folks in that avenue when it comes to the off-road, long travel, or non-race truck based stuff. There's another good shot of like that upper arm. You can see this kind of the style. This is one of his kits. This is good old-fashioned XLT long travel kit. I mean, this is some old school shit right here. And so, yeah, again, just another way of doing it. And I know there's some of these machined upper arms. We'll get into that next. I just wanted to review some of like what the long travel stuff, style and construction will look like, relatively speaking, and some of those variances. And it does create a very easy arm to make, so that is a plus. But he has transitioned into the other style. But yeah, so here we go. Here's another good shot. You can kind of see it's, very flat, simple setup that snaps together. This section for the bearing on the upper goes in place. Bam. Again, lower. Very similar deal. These are fucking GMT 800 long travel kit. Again, another old school fucking setup. Holy hell. Surprised he's still even selling this stuff anymore. That was a few years ago, but still. Just older trucks. Trucks that were cool when I first started. Not so much anymore. But whatevs. That's just how it goes. So yeah, and now let's move on to let's see, slapper arms, fixture width, main pivots, and overlays. Okay, cool. So on upper arm stuff, well, any of the arm stuff, to be fair, and I don't think I reviewed this too much, you always have to do the best you can to predict movement of the arm and components after welding. So it's not necessarily a bad idea in some of these situations to intentionally design the arm where the pivots, so to speak, on the chassis side are wider than the actual bulkhead. And we're not going by much. You know, we're going to be going by like 20, 30, 40 thousandths, maybe a 16th. And what I'm referring to is these pivots here. So you would intentionally have those wider in the computer or wider in your fixture, because when you weld this up, typically speaking, those like to shrink inboard, not outboard. And so you'll intentionally give it 20, 30, 40, 50, 60 thousandths of movement in there, and so that you're predicting that once it cools and you bolt it out of the fixture, etc., that he's only going to dance a little bit inboard or a predictable amount inboard and line up bitching with your bulkhead. Now, there's obviously a lot of variables in that too. So I would say the norm would be 30 to 40 thousandths, but I have done much higher than that, like 60 to 80 thousandths, depending on the specific client's preference and how they weld the arms up, what the arms are, style of welding, style of tooling they prefer, and they just tend to warp a little more. And so we have to account for that. Now, if you're going to be stress relieving and heat treating them, things like that, again, I still build a little bit of that into it as well. But you just got to watch for that. If you're doing it perfect to the bulkhead, so to speak, from computer to fixture to bulkhead, more often than not, you're going to find that when you go to bolt that arm in, it's going to be just a hair narrower than the actual bulkhead. And this can obviously become a headache. And so you may have to shave or custom machine the spacers to get that to align properly, like 20 thousandths off here or there. Another way to mitigate that is you build the upper arms out, like in this setup right here. This specific setup is a buggy setup where the rear upper arm, the front upper arm pivot can slide just a hair. There's a bit of movement in the front upper arm pivot on the main tubes that hold that part of the bulkhead, so that we tell our customers they weld this arm up, get it all bitchin', and then they use the arm to set the upper arm pivot in the chassis to make sure that that's kosher. So there's another way to mitigate what I'm referring to as that movement in the upper arm by finalizing your chassis pivots to wherever this arm cooled and shrunk to, so to speak. Or you could do both, or you could do all three. You could do a little bit of spread extra in the computer. You could do stress relieving and heat treating, and you can also then final set the bulkhead mounts to be like super fucking anal about everything. And I've done combinations of all of this in different applications and scenarios. All I'm saying is that what you don't want to do is you do not want to assume that the arm itself is going to maintain that same chassis spread that you design into it post welding, because it rarely fucking happens. I mean, they always squeeze some amount depending on how much of an asshole you are with welding. Is going to vary. Like if you just fucking MIG weld the shit out of it, crank the amps up and turn and burn that bitch on a table, she's going to noodle a fuckload. If you take your time, multi-pass it with appropriate spreader built into it, appropriate spread built into it with the computer, and then have it treated, etc., most likely she's not going to dance very much. So there's ways to mitigate it, but obviously the methods of mitigating that spread movement increases time and cost. So with everything, you'll see this theme in off-road. Well, everything in racing and in life. The more you mitigate potential issues or headaches, so to speak, you're always going to do two things. You're going to increase time and you're going to increase cost. Where you draw the line on that, I can't fucking tell you, because everyone has their own opinion. Everyone has their own method. And to be perfectly frank, there are methods that are a little bit more quote-unquote redneck, so to speak, that do just fine, where other builders are like, that's total bullshit, and vice versa. While there's still guys that will be like, oh, going all these extra steps is just a waste of money. It doesn't do nothing at the end of the day. Again, I understand and see the arguments for all of those things. I tend to be in the realm of where it's appropriate and when I do have budget available to do so. We definitely push clients to use some of these mitigation tactics to make the components a little better. And that is always going to yield a better product. But I understand that's not always the case. So just, again, something real quick on that weld spread of the chassis pivots and, trying to mitigate any potential issues. Another thing, too, that was that I have a note here for is holes for welding. So you'll often see holes drilled into arms or laser cut into arms in what seem to be random places to some degree. And this is gas accumulation mitigation, so to speak, especially with like treated components and things like that. So like in this specific example, so some of these holes obviously are going to get covered up by cup wraps, but they also play a secondary role in that they allow welding gases to leave the hollow component that's getting sealed, because basically these end up with like the sealed section. And so in that fashion, there's a few ways to do this. You can do it kind of like this, where obviously there's some area to vent, or you can take like an 1/8 inch drill and drill that those vent holes. Now, if you're going to go treating, etc., you got to drill some vent holes in it anyways. So you might as well do that. Now, typically when I'm designing stuff, I do not put the vent holes in the CAD files for two reasons. One, for some reason, it always pisses off the fabricator, etc., because they're not in the fucking spots that they want them in, or they're not the diameter they want, because everyone has their own theory on, is a fucking 6 millimeter hole fine? Is a 3 millimeter hole fine? Is a fucking, 3/16 hole supposed to be what you use? You see what I'm saying? Like it doesn't matter. As long as you're venting it, you're venting it. Maybe like a fucking 25 thousandths diameter hole is not enough, but I got guys that do like fucking 3 millimeter drill bits, and they're totally fine. Punch a few holes around the hollow sections, and then what you can do is when it comes back from heat treating as well, you can go ahead and TIG those up real quick and sand and flush. You never even fucking see them. But the point is, you got to have some gas venting of some sort in these sort of hollow arms to some degree, because it's going to get you that fucking blowback if you don't. So this is kind of like killing two birds with one stone, because this is also where the wraps are. So the wraps are going to cover these. But at the same time, like that's definitely venting those hollow sections appropriately to allow for the reduction of that build back. And so like in an arm, like let's say we were going to, do this arm and treat this arm, I would drill, probably a hole underneath here, a hole, because these are wraps, a hole there, and similar on this front side too. And that'll help vent out all that stuff. So when you guys are seeing those little holes, like 1/8 inch holes drilled in stuff, or random little holes like that, it's typically not to lighten the material. Those are in place for gas accumulation mitigation of those hollow sections of the arm during the fabrication process. And typically speaking, that is almost exclusively to TIG welding, not so much MIG welding. The MIG welding, it's so fucking fast and does not really push a lot of that inert gas into the hollow structure. So you don't really get like that blowback, so to speak, that you would see with these TIG situations where when you're multi-passing stuff, etc., I mean, it can throw a lot of fucking inert gas into that hollow compartment, and you got to mitigate that somehow. Otherwise, you'll know it. It'll eventually, you'll just go along and it'll just fucking kick right back at you and just blow out your fucking TIG weld. And next thing you know, you're no longer an Instagram fucking welder because you can't take a picture of it. So therefore, it's fucking pointless. You might as well throw the arm away. So yeah, quick little tangent on that. Weld with for weld warp. Yeah, I went through that. So machined upper arms. Again, another cool fucking part. And we're starting to see a lot of this more and more. And there's a few ways of doing machined upper arms. Let me close out. I have too many things open. It doesn't want to do that. Fail. Bear with me. There we go. Okay. So let's go through. Oh, these are all lowers. Sorry. Brain fog. Upper arm. So machine upper arm bits. Okay, but before we dive into some of mine, let's review some more traditional stuff. So Blitzkrieg, Nate, he's definitely been doing machined upper arms for a long time. And so when you're doing machined upper arms for like the big truck stuff, etc., here's a great example. There's a few ways of doing this. And so you got to, again, everything comes down to cost, mitigation, headaches, time consumption, style, and preference. So let's review a few facets. First and foremost, there's two. There's kind of two avenues to start with when you're talking about machined upper arms, and that's flat and non-flat arms. Right off the bat, a flat arm is going to obviously be cheaper to machine. It's literally just a flat chunk of material, so that if my arm, like in this case, Nate's, I believe, are 1.5 inches tall or thick, so to speak. It's basically just a piece of 1.5 inches like stock, and you're milling it top and bottom and done. So there's no three-dimensional contours that would make that starting piece of material significantly more height-wise. So like, a 2-inch piece of material or a 3-inch piece of material to machine that arm. So this is a cheaper way of doing it, but there's trade-offs with everything. And so again, one way of doing it is a flat arm. The other is having the arm kick. In other words, like this arm right here has a kick in it. So the starting material is much thicker, but now my bearing cup and everything match appropriately to the upright through travel. Now, in Nate's case, in this arm here, he runs a vertical bearing, so it's irrelevant because I'm running a horizontal bearing on that other arm. So to appropriately get that, I'm starting with like a 3-inch thick piece of material and machining that down appropriately. And the entire arm is machined, as opposed to like what he's doing here is he's got a chromoly section of plate that bolts into the arm that then captures both a bump pad, you can see his bump stop hanging down, and captures the upright section for the bearing for the upright section. And so again, a different style, so to speak, and a way of doing like a 2-piece arm in machining. Here's another look at it, a fabricated end section to machined upper arms. And so that's one way of doing it. Let's see. Stewart's Raceworks. So they do a flat arm too, and I'm pretty sure he is running the big trophy truck bearing in his flat arms as well. Yeah, so here's one of his arms. It's not a whole picture. See if he's got a better picture somewhere. Oh, that was the all-wheel drive one that he did. But see, he's machining them flat, so to speak. So the arm itself is flat to the bearing, which again, if you can get away with that relative to travel, it's plausible, because that bearing and the upright connection obviously move, and that could hinder in one route or another depending on how you have the characteristics of the suspension set up. And so he's got it, for obvious reasons, mitigated to where he can run that flat arm. Let me see if I can just Google that. Stewart Race. There we go. Of course, the picture is not on the side I was looking for. Yeah, so you can kind of see what's going on here. So this arm is a flat machine, a little bit more old school in style, but again, that doesn't mean there's anything wrong with it. And then there's no kick to the bearing to match the caster or the camber curve, so to speak. But most likely than not, he's running a very big trophy truck bearing in this, and he's probably just fine in relationship to the upright and bearing pivot geometry, to where he's just barely maxing that out at extension would be my guess, to where he doesn't need to mitigate it any further by angling that bit to be the bearing perfect with the upright to maximize those bits. And so the inverse of that, or flat, would be like what I have here with this arm. Now this arm is definitely a little bit more on the robust side of the table, and I'll get to that in a second. But let's look at some other variants. Triton did, Igor did one that did have a end that was fabricated as well, but not the same as Nate's, but similar to Nate's. Let's see if I can pull that up. There we go. So this is a machined arm, and then this is an end that is machined fab, whatever you want to call it. It's not aluminum, that clicks in there that holds the bearing cup. It might be fabricated. I can't tell if that's a little plate work assembly or not. It might be a little machine piece. But the point being is it's two. It's a machined aluminum chunk and then that end chunk, so to speak. And he is running pinch bolts on that side of the table there. Pinch bolt with this a locking nut, so to speak, to hold that appropriately. Again, it totally could be overkill. I mean, it's cool. Definitely on the gnarly side of the table in that regard. And then here's the section that transitions to where the bearing cup, for obvious reasons, is not flat to that aluminum arm like I was just referring to as well. And this looks like it's more of a machine piece that slides into the aluminum arm to some degree and bolts in place. But yeah, so again, another different style in that. Yeah, and then now we can talk about some of the inserts. We'll go over the chassis side. So those are some variables with the bearing cup side of the table. Another bearing cup variable is, in other words, this is aluminum. And then let me see if I have an expansion. There we go. And this is our bump pad that slides down into this piece. We have an O-ring here, and it's a cap that also doubles as the bump pad. Now, this specific arm, the bearing presses in from below, so the snap ring is underneath here. In this specific arm, it's going on a very heavy crew cab pre-runner. So this arm was done a lot more in the robust fashion by request. So in these applications, I obviously like to go a little bit more with the bolt head on this. And the reason is, if you look closely, I have a very small lip on this guy that actually gets pressed into the top here and holds the very interior edge of that bearing race. So it's transferring load directly from the bump stop into the race of that bearing that's pressed in there. And the reason I've done this in the past and just did this recently is on these big, heavier pre-runners, I have seen these arms crack here when you're using the top of this as the bump pad, so to speak. And so to mitigate that, I have done this. Now, is it necessary for like race truck stuff? No. But again, the pre-runners that, in essence, this was designed to eventually go on and that I've seen in the past are crew cab big pre-runners that are, thousands of pounds heavier than like a trophy truck. So you'll see other variations of the same style where it's just a straight cap that goes on top with just a few bolts. We just went a little bit extra mile and create a little bit more robustness in this specific scenario. And that cap can be like 17.4. It can be treated chromoly. It can probably be just regular chromoly. You definitely don't want to do it on mild steel or aluminum. So like 17.4 chromoly would be like the preferred materials for the cap, and then the arm would be aluminum. Some guys would be like a 6061 T6 or something, or I kind of like the 7075 stuff myself. But again, everything has its own cost and application depending on the client. But just another thing to show you like different variations of machined upper arms in relationship to the bearing cup. So you have like that one that Igor did, where it's like the machine part that slides into the arm. You have like what Nate did, which is a fabricated section onto the machine arm. Then you have like a full machine arm, like what Stewart's did, kind of what I did here. So, a few different ways to accomplish the same task with machined arms or machined upper arms. Now let's focus on the chassis side pivots. And there's a few different ways of doing this too. So like on Igor's example here, he's doing a pinch bolt with a lock nut that would not be a traditional jam nut, so to speak. But what this basically is that piece, if I remember correctly, I'd have to ask Igor, but I'm pretty sure that piece, this collar, actually threads into the arm, then jam nuts there, and then the collar jam nuts. And the collar is probably like a 17.4 going into that aluminum piece. So it acts as like a double pinch bung collar deal. And the reason you're doing this is to avoid having the rod ends directly thread into the aluminum, because the 7/8 fine thread arguably is not the best thread to be going straight into that aluminum block. You want to mitigate any issues you see with an aluminum to that thread surface because it could pull out the threads. So what you would want to have is a larger diameter, coarser thread engagement that goes from your machined collar for the rod end into the aluminum arm. And I believe that is what Igor is mitigating in this. Arguably overkill. I mean, it's not going to fucking go anywhere. That's for sure. But I think that is what he is doing in that specific example. So you're not, and I do very. I think Craig did too. Let me look at Craig's. No, because you want to avoid threading the rod end into the aluminum. That's like the worst thing you could do for these upper arm assemblies. Like I'm saying, you're just asking for those aluminum threads to fail. Hull designs. And I'm pretty sure Craig did this on the Herbst arms too. Let me try and find it. Here's a good example. He did. Yep, this is exactly what I was referring to. So these are most likely 17.4, and he got the weight down pretty good too on this. Yeah, this is a Herbst upper arm, and this is exactly what I'm referring to. So these are most likely 17.4 that thread into that aluminum arm. And again, he's got a cap that goes on here for the bump stop. And this is what I was just referring to, where in that one I just showed you, I intentionally made mine like way more robust per that client specifications and those trucks. The truck this is going on is like half the weight of the truck that arm I was just showing you is going on, to be perfectly fair. You know, that other pre-runner is pushing like 10,000 pounds loaded. These guys are probably close to 5,000 pounds realistically for these specific Herbst platforms. But again, he's not threading directly into that aluminum. Excuse me. He is using a mitigation of using, and like I'm saying, I'm assuming this, Craig can probably correct me, but I'm assuming that's a 17.4 insert. That is what is holding that 7/8 fine thread of the rod end. And then you have a larger thread, diameter, pitch, etc., that is then going to engage into the aluminum and give you a much better robustness, so to speak, and significantly decrease the probability of de-threading that aluminum chunk. And that's what it looks like he's doing here. You can see in these pieces, obviously you're stepping from this larger thread to the smaller thread in this fashion. And this is a good way of doing it, and this is definitely would be more proper as opposed to just straight threading that rod into the aluminum. And now I can show you what I have done. So in this arm, it is similar. We have 17.4 inserts and a little jam nut there. And that insert, here's a perfect example. So these inserts thread into the aluminum, and then I actually have set screws that come underneath that grab a surface that is machined at the end of those threads. So they bottom out in the aluminum, and then we have a set screw that holds it so it doesn't want to back out at all. And then the jam nut and rod end go in just like it would a traditional arm, so to speak. So I'm mitigating that issue I was referring to, and I'm also mitigating any of the, basically that wanting to back out by adding that set screw in to that arm. I wonder if I have any other pictures of that set screw. I don't remember what size it is off the top of my head. But again, just a way to mitigate any potential issues in these sort of applications by not having the rod ends directly thread into the arm itself, and by having the arm sort of this nice little robust assembly to then have the rod ends thread into. Just something cool that we've done, and obviously others have done. Again, I'm not the first person to do this. I won't be the last. I am by no, and that, like Craig's not the first one to do this either. I mean, this has been done many times over. Way past my experience, so to speak. So that's a good ending for the upper arm fuckery, and we can move forward. Let's see where we're at on time. A little over an hour. Cool. Let's move on to some stuff with uprights. So we'll dive into rear wheel drive uprights first. and some of that stuff. But yeah, so I am out of water. One sec. It's just like dry as fuck in this office. Whatever. That's just how it goes sometimes. Okay. There's a bunch of different ways to do uprights, rear-wheel drive uprights. Arguably one of my favorite categories because there's so many cool things you can do. Different styles, concepts, things like that. So let's start with some simple stuff. We'll start with the cheapest, so to speak, or some base level stuff. Let's see if I can find it. Here we go. These are some very simple plasma table friendly uprights. Cool. This is like a sand truck assembly. So these are, sold on DIY Off-Road under some of our sand truck bulkheads, etc. They're just flat plate, Oreo style, click together, plop on a snout block or a faceplate, so to speak. And obviously there's tons of different variations of those. Like here's our truck ones for our, look at that fucking, how's that for fucking CAD, shanking fucking threads in the middle. Oh, that's funny. But the point being is you're slapping on a snout block. This is a machine snout block. Now, the cheaper stuff per se, or the more budget-friendly stuff, you guys will be laser cutting or water jetting faceplates, snout blocks. We've seen that, especially in like the long travel stuff where they're doing unit bearings. We have seen that where it's just laser cut sections for the upright and the unit bearing bolts to that. And these uprights, these are like plasma table friendly stage 1 uprights that would be like for our truck front bulkheads. And they use a machined snout block that I actually sell. So shameless fucking plug, huh? And I do these out of 1 inch thick 4130. They are the 12 bolt standard pattern and spread for pretty much everyone's 2.5 inch bearing race hubs, which you'll see all over the place. And they're machined out in the front to match the hub, so to speak. This one's a little dirty, a little dusty. And in the back of it, I have machined out as well. And that is so you can appropriately tuck that bearing cup right up against that bad boy to get you some of those geometry characteristics that are favorable. So this is, again, an Oreo style plasma table friendly deal that just snaps together and turns and burns with what are snout blocks. And it's a good way of doing it because the snout blocks are 1 inch thick. Typically speaking, we rarely ever see issues with guys warping them because the plate work that's going to this at most is like 3/16. A lot of times it'll be 1/8 inch or 3/16 for these lighter duty applications. In some of these plasma table friendly truck stuff, it'll be like 3/16 4130. But rarely is it going to be thicker material. Maybe quarter in some uprights, maybe for some sections. But that is a good, entry level-esque upright for like truck based stuff. That's a stage 2. Let's go to some buggy entry level stuff first. Oh, here we go. These are the Cartech uprights. They're a fabricated variant. Now, to be fair, Pro-Am made and sold these first before Cartech has their own house brand, so to speak, and Roy separated from Cartech a while ago. But he does sell, Roy does, Pro-Am. They have their own line of uprights that are just like this, which are laser cut, water jet-esque faceplates for like a 2 inch snout that gets welded in, and a very simple welded clevis with like a tube main section and then plate work. And you basically take this piece and put your steering mount onto that. Again, these are very good buggy-esque entry-level type of upright assemblies. We have a bunch of guys that run these in that fashion, and it's really hard to argue. They are a pretty good bang for the buck. And both Cartech has a house brand you could purchase directly from them. Also, if you call Pro-Am, Roy has a series of these as well, which are arguably identical to the Cartech ones because the Cartech ones basically are just a rip-off of what Roy did. But to each their own. Now, that is a very basic way of doing this. And so let's move forward with a step above and go into like more the snout block style. So this is a snout block style upright, one of our stage 2 kits. Now this one is a little bit more unique. So looking at this head on, you'll notice there's like this weird kick in the whole upright. What this is it is locating so the upper and lower arms are built with the spherical bearings being perfectly straight in the arm. So when you have caster in the assembly, something is going to be angled. So if I have a straight upright, now the bolts are going to be angled. Or you angle the cup in the arm, and then that will straighten up to the upright, so to speak. Well, in this situation, I have this sort of kick built into the upright to match the caster so that the bolts are perfectly flat relative to the upper arm, top and bottom, upper and lower. Just another style of doing it. No, I'm not the first person to ever do this. I don't remember who I saw do this prior, but I have done this before, and I have seen this before I did it, definitely. And so this is one way of doing it. As you can see, there's that kick, and in this specific one, this plate right here that holds the forward side of the upper arm pivot is actually the same plate that holds the rear side of the lower arm pivot, and then I bend it and bring it in, and then all the plate work comes to it, so to speak. And then this one runs that same snout block that I was explaining. And here's a fixture for this as well. You can kind of see how I like to do the fixturing for these. It is a mirror image, so like the inverse side would bolt to this. This guy would shift to that side and bolt there, and then you would build it appropriately. Obviously, there's spacers in here that hold these spreads. They're just not in the computer. Now, let's go to, here's another stage 2 upright in that same fashion. This one has a steering pivot, obviously a lot lower. This one's actually for swing set steering. And again, very similar how I have this kick built into it for that offset in the bearings and the upright. So this one is offset 6 degrees, and there are 4 degrees in the bulkhead, giving us 10 degrees of caster. And so now my bolts are parallel to the bearing at static. I hope that's not confusing. As opposed to an upright like this that is straight, obviously at caster, those bolts are going to be at that degree relative to the bearing pivot if the bearing cup in the arm is built straight, the vertical bearing to the arm, which most of the stuff I do, most of the arms we do in that fashion are done that way for simplicity. Once you go to horizontal bearings, I do start to kick them all funky angles, and those are inherently a little bit more complex to build, but again, not the end of the world. So, and the stage 2 stuff as well is an on-edge weld upright, so it's a little bit more complex with bending and forming. Obviously, a little bit more cost incursion with doing the tooling and fixturing appropriately to get this done. So just like everything, you start to stack on complexity. You're going to start to stack on time and cost and those other factors. And these are both what we call snout block uprights. So this is a snout block. It's this machine chunk where the hub snout will bolt to. And that is one way of doing it. So stage 2, stage 3. Now going to more horizontal bearing uprights as opposed to the vertical and the little bit more expensive stuff. You start to get into things that are more clevis-based uprights. So let's see, find some. Go back to the front. Like here's one. There was a class 1-esque deal that we did. It is a clevis based with a weld-in spindle or weld-in snout. It actually presses in, and then you get a weld bead around it. There are full press-in ones, which I'll get to that too as well. But right, there you go. There's that deal. And so this is a machine clevis on the bottom, and then you have an upright assembly, so to speak, that matches your inclination angle. So the bearing bolt for this clevis is at an angle that would be your inclination. And there's obviously, if you watch my previous episodes on inclination angles and things like that, there's a ton of variability in those and how those are machined. Now, to go with something that is a non-inclination-based clevis, Nate from Blitzkrieg makes those. I have used those in the past. So this is his clevis, this bottom chunk right here. And this is one big machine chunk that is the bolt is vertical. So instead of the bolt matching inclination angle, it's vertical. Again, different strokes for different folks, but Nate builds his trophy truck uprights with a vertical bearing up top. So he doesn't necessarily need that inclination mitigation, so to speak. This is an upright I did for Ross King in the fashion that he preferred, so to speak, or requested would be another way of putting it. And it's a vertical bolt here. And so we just have a little cubby to encapsulate that nut that goes in there above that deal. And these two main ribs that get welded up and in also encapsulate this machine block that we did for the top. Again, this was a style that he suggested / preferred when we did this back then. So this is a clevis that's a non-inclination based clevis. And another company that does these sort of clevises is Pro-Am. So you can buy, and I've mentioned this before on previous podcasts, you can buy upright assemblies from Pro-Am. Let me see if I can. I tried to Google it last time, and Roy does not have a good website up. I wonder if their Instagram might have it. So I know Craig has used Pro-Am stuff before. So you can buy upright setups from Pro-Am, and a lot of guys do use them. No posts yet. Go figure. That's funny. That's right. Roy is selling at Mackenzie's. A lot of guys do run Pro-Am upright assemblies and hub assemblies for that matter, but uprights is what I'm specifically referring to right now. Here's one on Pro-Am hubs. Those might be Dave's uprights, though. That might be Dave's uprights. So that might not be a good example. Might be Pro-Am hubs on that Stronghold car. Anyways, I know that it's not the best example because I can't find what I'm looking for, and I've mentioned it before. I have the CAD files for them too. Herb Smith Fab, I think, is using Pro-Am uprights. Let's see if we've got any pictures of theirs. Of course, there's nothing. Turbo Hearst Motorsports. The point being, so if you're not doing the baller-esque stuff or going in the direction of full kill trophy truck stuff, Roy at Pro-Am does have a series of uprights in various levels, sizes, and fashions. Like I had said on previous videos, one that would be like a standard Class 1-esque clevis is a 5.9 clevis upright on like a 14 degree, 12 degree, etc., and 14-inch spread. And he sells them in that fashion. And I've reviewed some of those bits. I just don't know of a place online or good examples of what he has available. You'd have to talk to Mackenzie's or just go directly to Pro-Am, try and talk to Roy. But again, typically speaking, the guys running this type of stuff are going to be more race truck-esque stuff, although Roy does have those more budget-friendly uprights and things along those lines. But in the race truck environment or the more serious environment, he makes a really nice clevis style upright with the appropriate center section and the plate work to match if you don't want to make your own. And we have a lot of clients, they're on both sides of the table, that would make their own, not make their own, or buy them. Here's a good shot of their upper arm. This is the Landshark Classic machined upper arm, and another format of a flat arm to some degree, even though this is very, very old, relatively speaking, for the off-road community. That truck is like as old as I am. But anyways, so going back to these clevis style deals, you see variations of these sort of clevises in different formats and styles. And what they all boil down to is you're going to have a bolt pattern of sorts that will appropriately reflect what hub assembly you're going to run, and then you're going to have an inclination angle that would match that. and stuff like that. Now, this is a bolt-in deal, clevis, with this section up here has a machined chunk that is hollowed out for nut capture, so to speak. And then the top has a spud that welds in. And I'll get to those in a second. Right now, we're just talking on the different forms of the clevises, so to speak. So this is one form of it. Now, the Pro-Am ones, they have the brake caliper bracket that bolts into it as well, similar to like this machined upright I did for a luxury pre-runner client a little while ago. The bracket bolts onto the face as well and captures the bolt-in snout. And this is all 4130 with tabs that weld on, specifically requested by a client for something that's far more in the robust category, just gnarly robustness. It didn't end up being terribly heavy. You would think it would be insane. It wasn't bad. It was a little bit heavier than like a standard fabricated heat-treated upright in this fashion. So it's not like it just killed the whole front end weight-wise. But this one is machined, and then this piece is obviously machined, presses in, and then it gets plug welded in, and then circumference welded at the top, and then treat the whole assembly. But yeah, let's focus on those the clevises. So we reviewed snout block. Let's try to see what else we have in here clevis-wise. So here's another version of a trophy truck upright that's a snout block form, so it's not necessarily a clevis, but it uses machined pieces in here. And this threads in here, so to speak, and it's plate work that encapsulates the snout block and then holds the section of the upright. And I don't have a great image of that, but it's a bolt-in snout assembly, and then this is a chunk that welds in. So again, it's kind of a mixture of like a snout block clevis-esque deal, but it's not a true machined clevis like some of those other uprights that I was showing you. Now let's get into some of the more, and so that's all bolt-on based stuff. That looks like they might be doing a press-in snout on that, or a press weld snout on that. That was an Armada one from a while back. Again, another clevis. Now here's ID. These are press-in snouts. So in essence, and I've asked Dave about the robustness of the snout assembly, like if that was the consumable, and he seems to be more on the impression that, with his experience these days, or in the amount of time and experience he's had, he has seen far less snout failures and more upright failures. So in other words, the snout gets pressed into this upright from the inside, and then obviously your hub assembly goes on and stuff like that. And the argument could be that they might want to twist and stuff, so you might have to tack weld them. Again, just more of a prep trick, but they're not welded in snouts; they're press in snouts. And you could do a similar format and then weld the snout in too. I've done stuff both ways. For like full kill race stuff, I really do like this. They are more expensive, so to speak, and more complexity, but you can end up with a lighter setup overall. And even with that said, like Dave runs smaller front hub bearing kits as well. And so like that's another, well, we'll get to the hubs here in a second on the upright stuff. But again, this is a press-in style as opposed to a bolt-on snout, etc. And another great way of doing it. We have a 6100 truck I'm working on designing that we're not going to get to or that one won't be hitting the dirt anytime soon because that specific build process has a few in front of it, but is running that press-in deal from ID. And the goal in that is to a very lightweight setup. But another way of doing it is like Dave has his own bolt-on one. Now, to be clear, so this is what I have here is a standard. This is a standard 12 bolt. So this is smaller. This is like a 4-inch deal. So it's more of like the norm with front snouts. Now, Dave is a 5-inch pattern on his, so it's a much bigger bolt pattern for this chunk. And these are post heat treat, and then he machines the surface for the upright engagement onto the bolt-on snout. Now, to be fair, this is heavier than that press-in that I was just showing you from Dave. So there's one trade-off right there. A bolt-in snout versus the press-in snout assembly. To change a snout on this, you can do it with the upright on the car. To change a snout in the other application, you have to pull the upright off the car and press it in. So there's a trade-off right there. Like here's the example. These press in, so obviously you can't have it on the car to press that in. The lower arm is in the way. And so that is part of the headache with that, so to speak. But everything has its own variation application. The vast majority of guys are running snout block type stuff, and it's totally fine with that bolt-on deal. Hell, there's still a lot of guys running weld-on snout applications, one for lightness and lighter duty-based stuff, like 2-inch hollow snouts, etc., that are welded in, like on those CarTech uprights, or like I did in this application here. Let me see if I can find it. This one right here. This is a welded 2-inch snout on a very lightweight 7200 platform. So again, different strokes for different folks, and as a very small brakeman caliper too. But again, we have a much lighter vehicle in this specific 7200. I mean, arguably one of the lightest 7200s that may have ever been built per se. It was our goal on that application. And so this is all just different. This is a weld-in snout, all just different ways of accomplishing the same task in varying levels of cost, varying levels of weight, varying levels of skill sets required to build these. And so Dave does it this way. I don't know if Pro-Am does a press-in snout. Maybe Craig can answer that. I don't know. I certainly have not used press-in snouts from Craig. The only press-in stuff I know of that our guys have used is going to be coming from Dave in that fashion. And then bolt-on snout stuff, well, that is all over the board, like I was saying, total variations. So that would cover, in essence, the different styles of the snout blocks and clevises. And fab saw. Okay, and then on like this one, yeah, you can kind of see, like here's this machine tube, so to speak, with the plug welds. He gets machined in. Then this is our spacer up top. It's a 4.5-inch trophy truck bearing, so one of the big boys. And then these plates get welded in, and then it gets covered up. Pretty robust assembly. And this is a very heavy truck. This one is going on specifically. Let's see. I think I have there's the tooling piece for that. We cap this guy to cover him up so you don't get that guy fucked up. Circumference weld him to this guy with the proper chamfer. So you're multi-passing this stuff big time. And then in here we've got the setup for the steering, and then here's our clevis that bolts down. We put a spreader in there. This guy gets welded into the clevis. The top of the clevis is machined to accept him, and then there's the bolt head deal for the bottom. And again, totally a ton of variations in that stuff too. Hubs and options. Okay, cool. So 12 bolt race hub stuff. We can go through some of that. So the common stuff is like, let's see. I keep referring to these 12 bolt snouts so that everyone understands what this stuff is. Like Nate makes a bunch of these hubs. Let's see here. Rear suspension, rear end housings. I wonder if it's in their housings. Where are your hubs, bro? Oh, here's a snout clevis. This is exactly what I was referring to. This is Nate's deal. This is what I used on the Ross King deal. Yeah, 12-inch on 4-inch standard. Same with 6 bolt. Dana 44 stuff is where this derived from. Here's another version of snout blocks. This is a version he used, and I think he originally did these in like an F-150 kit back in the day, but it uses that pattern. Maybe he is not making hubs anymore. Oh, there we go, hubs. He definitely is making hubs. Okay, so these are what I'm referring to with the snouts. So these are 12 bolt snouts, and they bolt into, well, it's 2.5 spindle nut, 2.5 race hubs. There we go. So these are what would bolt to the front of that upright. This is that pattern that you're seeing here, and that common 12 bolt pattern. These are considered race hubs, and this is a 2.5-inch bearing hub. Most of the guys these days are making 2.5-inch bearings hubs, which are to some degree derived from like the old school Desert Specialties type of stuff. And there's at least 24 companies that make these 2.5-inch bearing hubs. Nate's been making these for like 2 fucking decades now. Pro-Am has their versions of hubs as well that match their uprights, because I believe they have a different snout pattern, if I remember correctly. So Pro-Am uprights and hub kits, you basically buy them all together. And in this fashion, this is still kind of overkill. So like some of the race trucks will run, trophy trucks, etc., will run 2-inch bearing front hubs. Like Dave from ID, they're running smaller hubs. Like the 2.5-inch bearing is definitely overkill, so to speak. It's just common. A lot of guys run that. So I think it has become more commonplace. But let's see here. Here you go. Here's a 2-inch trophy truck front hub from Dave. So there's another thing that you could put to rest on some of that argument, that, you know, a 2-inch bearing front hub is plenty strong enough. This is the Geyser one, and I believe these are that stepped deal. Yeah, it's a 2 3/8 2.0. So the inner bearing is a little larger than the outer bearing. Again, an old school way of doing it, but still plenty strong enough. It's like I'm saying, anything in that 2-inch bearing plus range in a properly designed hub assembly is going to be fine. You know, there's trophy trucks running, competitive trucks running this stuff, and the argument could definitely be made that there's no reason to go above that simply because of weight. And if you're trying to reduce unsprung weight, things like this start to add up. Just like, well, if you notice a pattern emerging, so to speak, like every time I'm referencing the stuff from like ID Designs, etc., you're noticing that he is reverting to proper welding techniques, proper treating techniques, and weight reduction in aspects. Now, the inverse side of that, they're definitely the most expensive, so to speak, when it comes to these sort of components and fabrication styles and building. So the probability of you building stuff in this direction might be low simply because it's out of your budget constraint, but that doesn't mean that what you're doing is wrong. I'm just showing you variations of different ways of doing this stuff through the table, so to speak, so that you can see like what the baller stuff is relative to some of the more long travel or simple based stuff. So let's go to some of the long travel stuff. Blitzkrieg off-road. Yeah, let's go back to Nate's. Front suspension. Wonder if he's got... so that's... I don't think he has a long front suspension kits. There we go. I'm trying to showcase one of his like snout blocks for like the Silverado, so you can see what he's doing on his uprights. There we go. So here's another version or another way of doing it. These are two machine sections. So you have the machine section here that is what holds the unit bearing, and then you have this larger machine section that holds the brake caliper mount, and then they're welded together. And you might be thinking like, well, why is he doing that? Well, the simple reason is it's actually cost effective to do it this way, because to get appropriate piece of like chromoly that big, stacked that tall, you're starting off with something like this thick and egging it out. It would be like 4 times the machine cost, when he can do it in this fashion, MIG weld it together, and it's totally fine. So this is sort of like a hybrid way of putting machine pieces together and welding it to make a snout block that accepts a 3-bolt unit bearing, which is a GMT 800 unit bearing, or say a GMT 900 unit bearing, as opposed to a race hub, which is like this stuff. Now, you can find unit bearing-esque hub stuff. So in other words, the unit bearing is that stock hub assembly from the Silverado that's bolting onto that upright. And Nate and some other guys do make kits that are unit bearing replacement race hubs that bolt into those assemblies. I don't think he's making them anymore. Let's see here. I'm not seeing it. But yeah, I am not seeing those. But the point being is these are different ways of doing the same thing. Let's look at some of his other snout blocks. So the trend also you're noticing is that the machining of the snout blocks is obviously best, hence why I sell these machined ones, etc. These are surfaces and mating situations that always do, this is that one I was just showing you, that always do better with a machine surface to the snout of the machine surface. So like I said, in some of the budget-friendly applications, they will run laser cut material for this sort of faceplate or double stack it or triple stack it. I don't think that's a good idea. Not a big fan. I think if you're already going down this road, at a minimum, nut up for that cost, because it yields a much better product overall. And so now you've got a nicer machine surface here that is mating against the machine surface of the snouts. Now, even though this is a F-150 kit, this is a race hub setup. So this pattern here is that standard issue 6-bolt on Dana 44 with an extra set of bolts clocked. Again, standard, same as like these we use in all fucking I-beams and arms and uprights and a ton of shit, all over the place. In fact, yeah, so again, just different strokes for different folks. Let me show you, an I-beam upright that I use this exact same stuff in as well. Right here, boom. This is that same snout block in our universal I-beam uprights. And I'll do a section on I-beam stuff down the road, but again, this is a plasma table friendly, snap together-esque upright assembly for an I-beam truck that converts to a race hub assembly and runs that 12-bolt snout block. So now you get a good idea to the some of these deals. Let me see if I can find a picture of the... I realize I don't have a picture of the press-in snouts. Let's see. Suspension, trophy truck hubs, spindle snouts. There we go. And he does not have a good image of that. Dave really needs to update his website. Damn it. Let's just scope his Instagram real quick. So I just want to and show you what that looks like for a press-in now that you understand. What is this? So you can see the variation in that. Because it's definitely more uncommon. Not a lot of guys run the press-ins. Oh, here we go. The perfect picture. So this is that upright post-heat treat, post-machine, and this is that snout that is pressed into it. Now, this is the geyser one. So this is where they run that slightly larger bearing for the interior side, and then a 2-inch bearing for the exterior side. 2 3/8 interior, 2-inch exterior. And for obvious reasons, these are plenty strong enough. This is a long time ago. Fuck. But yeah, that's what the press-in looks like on those. And again, different strokes for different folks. Here's another good picture. Jimco, here's a good picture. So you can see from the back that is pressed in there. And now you can kind of understand what I was referring to, where in this fashion, you obviously have to have the upright off of the upper arm to appropriately install it. Can't really get around that. So again, there's part of your trade-off for that, but it's done properly. Now, the only downside to this is you don't want to know the cost. Holy fuck. I mean, you're starting to get up there. These fucking uprights are more expensive, like that entire long travel kit with hubs from Nate. But you're starting to get into like the Narkill race shit at this point. And yeah, so like I said, ID runs a 5-inch snout pattern, so it's a little bit more robust, his specific snouts. I don't see that on here, but you can just trust me when I say that pattern, his 12-bolt, is a 5-inch diameter, not a 4-inch. Bearing sizes for race hubs. Yeah, I kind of went through that. Like I'm saying, most are 2.5. Those geysers run 2 3/8 interior, 2-inch exterior. But ID's or Dave's trophy truck ones are 2-inch. I have not run the geyser ones. Obviously, that's a geyser platform. I have run 2-inch bearing ones. Like I got guys that run like that stuff from Dave. And then I have a ton of guys that run the 2.5-inch bearing stuff as well. And We have even done, oh man, I don't think I have the files on here, but I have done a setup where it was, let me see if it's on the website. Hold on. We used a Spider Trax unit bearing for the front upright, and that was a customer request. Stage 3. Let's see if I can find images of that. It's not on here. God damn it. We used a builder bell for a Spider Trax for a rear wheel drive upright. I will make a note to show that next time, because I think we're about to call it right now, because we're an hour and 50. And well, no, we'll keep going. I still got a few bits left to cover. Okay, so brake setup, hat, and replacement rotor. Okay, cool. So on the hub assemblies and hub kits, there's two primary ways to look at these. There's ones where the rotor can only be replaced if you remove the hub from the truck. Nates are done in this fashion. And then there's ones where the rotor is removed while the hub is still on the truck. So Pram does that. ID uses a hat that goes over the hub assembly. And then that hat can be easily replaced by just removing the caliper, as opposed to like here you go. And these come in different hat depths too. We're using this on a brand new 6100 truck. And so that hat can come off pretty easily during a race, so to speak. And so it makes swapping stuff out or mitigation of issues in the middle of a race easy to resolve. And so that's a really good way of doing it. And then the way Roy does it on some of his buggy hubs, Wi-Fi hubs, and things like that, the rotor can unbolt from the assembly as well, even though it may not be a hat. It's just the way it bolts onto the hub and stuff. And I don't have any good images of that, but those are just two variations of doing it, and you got to keep that in mind when you're buying this stuff. The guys that are typically involved with more racing, they're going to be leaning towards stuff that you're able to remove the rotor from the upright while it's still on the vehicle, as opposed to having a hub assembly where the rotor is stuck on said upright, so to speak. So again, just something to note and watch for. And now let's go into spud style, pin, bolt style setups for the top bearing of these sort of arms. And now what I'm referring to specifically cater to the horizontal bearing setups. So that is going to be where the bearing is horizontal. This is a horizontal bearing setup. Okay, so cool. Here's a perfect example. So this is a spud style. So in other words, this whole chunk gets welded into the top of the upright, this whole piece right here. And the reason I call it a spud style is because there's actually a machined top thread section that holds down the top cap, so to speak. And on these, I actually like to offset this so that the center line is offset in the bearing, just to help mitigate any potential issue for, in theory, the center point of force being in the section where the two spacers meet, so that it has this sort of large chunk it has to sort of go through. And then the cap goes on and the nut goes on top of him. Another thing is and that's kind of like a shear aspect of that. And then, pin it, so to speak, and it prevents that top piece from spinning with the nut after, constantly turning the bearing, etc., with these pins. And I'm not the first one to do this. You'll notice that ID does do that, those little pin things as well, and I'll show you that in a second. So that is a spud style. And then on these, like these CarTech ones, they have the spacer up top, and you TIG weld this spacer down, and that helps the shear of that bolt. So it's not just shearing on the bolt straight up. It actually holds the spacer that's welded to the uprights. So we're welding that chunk to create like a better, shear resistance, so to speak, from that bearing than just riding on a bolt and shear, back and forth. Here's another one that we did that's a spud style where this part, here you go, offset spacer with the nut. He welds to the upright a bunch, so to speak, with plug welds. And then that way it's, again, I'm offsetting the spacer. So the center point of the bearing is through this big chunk of steel. And this is an old Ross King one where this guy inset here gets welded, and then the whole thing gets welded in. So it's creating that sort of shear. This is old. Here's another one with a built-in bump stop pad on a race truck. You can see this whole top section is a spacer that comes down with a built-in bump stop pad assembly that hides the nut. This was a customer preference. I'm trying to remember whose truck this was. This is years ago. But again, it's a spud style deal with the spacer that comes down onto it. And I offset it in that bearing, so center point of the bearing is not on where the spacers meet. And so yeah, let's show you some of the and then like if you don't want to machine your own, like these guys are machining their own basically. Fabrication, high misalignment spacers. There we go. These packs, you can buy these from Dave at ID and use these in. Like I have a 6100 truck that's using this assembly right here. So this would be a pen style, or this is, yeah, okay. So what I was referring to is a spud style. This is a pen style. Now, the reason I was doing the spud style, or the argument for the spud style, is to help with the shear aspect of the spacer mitigation with the bolt and that side load. Now, if you'll notice, Dave has pins that index the top spacer to the bottom spacer. These top ones, I'm pretty sure, are 17.4. These bottom ones typically are going to be a treated chromoly, and these get welded into your assembly. He might even have that. He does not have that explained in here. Pin base is what he calls it. But here's the point. He has a bolt coming through, so it's a pin style. So in other words, the bolt is now threading down into the pin. A spud style is where the spud is machined, and then it's a nut that comes on top. So the inverse of a pin style is this style. It's a spud that's machined where the nut comes on top. So it's two different ways of basically completing the same task, and he is mitigating that shear effect to some degree by both welding that top in and having, see, that's a spud style, so to speak, with a nut that holds down on top. And he is mitigating that by this guy threads into there, and these pins index into the spacer. So that helps prevent those spacers wanting to help shear the bolt, so to speak, under an extreme load situation. And like I said, we have a truck that's using this stuff right now, and it works just fine. And he's got a version similar to the other version I was just showing you, where it is this guy, where it has a bump stop pad right up top. So you can bump right off the top of that guy on your upright in your assembly. And again, different strokes for different folks. This is just another way of doing it. And those are pin style as opposed to what I'm referring to, which is spud style. And spud style means that it's a nut that comes down. Now, in the way Dave does it is definitely more than strong enough. And so both of these do mitigate what I'm referring to and can be equally strong enough if done appropriately. The pin style or the spud style. Where we see the big issue with the variance in those two styles is the fact that on UTVs, you want to avoid the pin style where it's a bolt coming down into the. So on the UTV applications, we have to machine pins. Let me see. Wondering who. Let me see if Master Fab. He might have an example. I know like Summers Brothers does. So what I was showing you was like a pin style versus a spud style on the truck stuff. What you want to avoid for sure is you want to avoid just fucking, putting a spacer up there and just having the bolt and then, it's in shear on that bolt for the upper arm. That is scary to say the least. Spud failure. I don't want to throw anyone under the bus. I know who made those. I'm trying to see if he has any of the newer generation of the spud styles that he was using. Here's a pen style that he does. These ones we did out of 300M. This was a while ago. But you can see we offset it in there. A pen style deal for the 7/8, and these go in. So the UTVs use these sort of like pen clevis deals. And again, you can do those in a spud or a pin top, like I'm saying, where the bolt goes down, or it's a spud, so to speak, to where it's a nut on top, as opposed to like I think. Let me see if Geyser. Geyser Brothers. I think they used to do pen style, a spud style stuff back in the day. It's been so long since I've seen the Geyser stuff. That is not it. But anyways, like I'm saying, those are two different ways of doing it. If you want, I mean, you can, like I said, you can buy this shit straight from Dave instead of machining your own. We've got customers that like to machine their own stuff. We have customers that don't like to machine their own stuff. So again, it totally varies. But there's a variance right there in those two tops, spud and pin style setups, and then that offsetting of the spacer in the bearing. Like I'm saying, I do that, but I also don't always put those pins in like Dave does, so to speak, to help prevent that shear. You can see the two pins that index those. It also helps prevent shear, but it also helps prevent the rotation at the top that in theory could start to loosen the bolt or the nut. Because if that spacer on the top side starts to twist when you're turning, in theory, that could prematurely want to loosen the bolt or the nut that's up there. And that's what you don't want. You don't want the spacer it's turning. What you want is the bearing to move instead of the spacers. So that's a mitigation tactic in that fashion. It's obviously more expensive to machine it that way, but that is a proper way. Like, yeah, here you can see the pins. That's what I'm referring to. Those guys right there. But yeah, so again, different strokes for different folks. So yeah, I think this is a good point to stop. One, because I forgot images on a few bits, which I will bring up next time. And we are already a few hours in, so we're going to pick up more of this stuff with machined rear-wheel drive uprights, and then we'll go on to all-wheel drive upright bits. So yeah, this has been episode 7 of JEHC. Just moving forward, just tons of information to go over, lots of cool stuff that we can review. And hopefully you guys are learning something or getting a better understanding of some of the aspects in this industry and some of the things we do and utilize for design and development of all this different stuff. So if you guys have questions, concerns, let me know. Admonish me in the comments. My name is Jason, owner of DIYoffroad.com, tech consulting, blah, blah, blah. And as always, gentlemen, pitter patter.